Okay, so in order to get the problems that we're working on right now, you need to know the formulas for kinetic energy, which is kinetic energy is going to be equal to 1/2 of the mass times the velocity squared. And you need to know the formula for potential energy due to gravity, which is going to be m, the mass times the acceleration due to gravity times the vertical displacement, delta y. And remember that delta y is relative to what you set as 0. There's another idea that you might need to know here, and that is that the work that you do, which is the force times the displacement, right? We'll just use delta x in this case, is also equal to the change in potential energy. Okay, so we're going to use these concepts together along with the law of conservation of energy, which says that energy is neither created nor destroyed, but only changes forms. Let me get this in here of energy. So how does that apply to us? That means that if you take the energy, the potential energy plus the kinetic energy, no matter where in the problems that we are looking at, they are going to give you a constant value. Now, in reality, we know that we're going to lose some energy, probably as friction, or there's going to be wind resistance or something. But in our problems, we're going to pretend we're in that perfect world where there is none of that. So let's take a look. Here is our problem. And we can see that right here, and I'm going to put this over here on the left. I'm going to break this into position A, B, and C. So let's start right here at A. And we see here that the potential energy with respect to gravity and relative to 0 here is going to be m g delta y, which is going to give us 100 times 9.8 times 45 meters. If you put that into your calculator, you should get 44,100 joules. Okay, but the object is not moving. So at position A, since the velocity is 0, the kinetic energy, and I'll put the numbers in if you need to see it, 1/2 mv squared, 1/2 the mass, which is 100 kilograms, and the velocity, which is 0. So that's going to give us a kinetic energy of 0. So what does that mean? That means that anywhere along this path that you are moving through, if you added the potential energy and the kinetic energy, they should always equal 44,100 joules. So at position B down here at the bottom of the hill, we can see that the potential energy is equal to 1/2. Oh, that's not true. It's the mass times the acceleration due to gravity times delta y. But at this point right here, delta y, this is 0. So we're going to have a potential energy of 0 at the bottom of that hill. And so there's 0 joules. And the kinetic energy should be equal to all of that potential energy that we had up here. We're going to get a full conversion of potential energy to kinetic energy. So that should be equal to 1/2 mv squared, which will be, we know it's going to be 44,100 joules. You could use this formula right here in order to find the velocity down here at the bottom. So if we solved for v, we should be able to get the velocity at the bottom of the hill. So let's see. Let's do some air algebra. So through the power of the internet and air algebra, the velocity that I calculated for the bottom of the hill is 29.7 meters per second. But what about at part C. Well, let's take a look and see what happens at position C. Slide this over a little bit and bear with me as I figure out FigJam. Okay, so at position C, we know that the total energy is going to be 44,000, let me fix that, 44,100 joules. But at C, potential energy is not zero. And kinetic energy is not zero. So we're going to have to add those both up together. So 44,100 joules should be equal to potential energy plus kinetic energy, where none of those is equal to zero. So the potential energy is going to be equal to the mass times acceleration due to gravity times delta y. And I think in the problem, I gave you the height here at C as 3 meters, if I'm not mistaken. So let me add that here. And if I didn't, just for the sake of example, let's just say it's 3 meters high here. And so that's also going to be equal to the kinetic energy, which is 1/2 the mass times the velocity squared, which is also not zero because the object will be moving. So let's take a look and see what happens when we put numbers in. And the mass is 100 kilograms. Oh, this isn't going to fit. The acceleration due to gravity is 9.8 meters per second squared. And delta y is 3 meters. And that plus, we got to add that to 1/2 the mass, which is 100 kilograms. You may have factored that out already. That's really your thing. And so I'm going to do some air algebra real fast. And through the power of the internet, there is your answer. If I was you, I would pause it and check your algebra. And that is how we find the velocity at position C. And again, the entire trip, the total energy should be 44,100, assuming I didn't make a dumb math mistake somewhere. Okay. But then we had this other situation, which was a little bit easier. Let me see if I can move this along. Okay. And let's draw. So we had an object traveling down flat ground. Let me get a pen. Oh, no, that's not what I wanted. It doesn't like me today. Oh, here we go. So an object traveling along flat ground, and then it travels up a hill and comes to rest. What would be the vertical displacement? The crazy part is it doesn't really matter what the angle of the incline is. The object will travel to the same height because it will have, so here's our object traveling along this way. Whatever the mass is, I don't know. I'm just going to make this up. With some velocity, we know here the kinetic energy is going to be equal to 1/2 the mass times the velocity squared. But since this height here is going to be 0 meters, we're going to set that as the reference point. The potential energy here is equal to mg delta y, but delta y is 0. So the potential energy will be 0 joules here at the bottom. And then the cart is going to travel up the hill and then come to a rest. And we're going to be able to find some vertical velocity delta y. I don't know what I gave you for an angle here, but let's just say that this angle is 45 degrees. Okay, fine. So this object is going to come up here and come to rest. If it doesn't come to rest, then it's not at the top. It's not at its maximum height. So we're going to say here the potential energy is mg delta y. However, the kinetic energy is now 0. It's equal to 0. And so I gave you an initial velocity. So there is some number that you can get here for your kinetic energy. But if in order to create the formula to make this happen, we know that all of the energy on this side will be conserved as it comes to the top of the hill. So then we say that 1/2 mv squared is equal to mg delta y, because all of the kinetic energy is going to be converted to potential energy. Here's the fun part. The mass will cancel out. So we get 1/2 the velocity squared will be equal to g, the acceleration due to gravity, times the vertical height as it goes up the hill there. And so we should be able to find a formula for the velocity here, which should be the square root of 2 times the acceleration times the vertical displacement delta y. That also works the opposite direction. So what would be the final velocity if you started it at the top of the hill and then let it come down? Actually, that's the formula I found here. Oops. That's the formula I found for the final velocity if we started it at a height of 2g delta y. I went the wrong direction here. But if we took this formula to find out how high it went, we would be looking for delta y, which works out great. So we could say that delta y would be equal to 1/2 the mass times the velocity squared. We can divide that by the mass times the acceleration due to gravity. These masses will cancel out, and that should give us 1/2 the velocity squared divided by the acceleration due to gravity. So this formula here will give you the velocity of the object if you start it at the hill and then let it slide down. And this formula here will give you the vertical height of how high it will go if it's traveling across the ground and then goes up the incline like that. Okay, so what? Well, then we have a triangle. So I think one of the time you'll see that the question that a lot of times you'll hear is, well, how far up the incline did it have to travel this way, right? This value here. Let's call this, I don't know, call this x, delta x. Okay, well, let's see. Now you have this triangle that you made, beautiful right triangle. You're going to have a value here for delta y. You're going to have an angle, not to scale. This is 45 degrees. If we go back and take a look at SOHCAHTOA, and we have the opposite side, and we have the hypotenuse, that's going to be the sine value. So we know that the sine of 45 degrees will be equal to the opposite side, delta y, divided by delta x, which is what we are looking for. We do a little air algebra, and that will become delta x is equal to delta y, which you found already, divided by the sine of 45 degrees. We are not spinning in circles, so this is in degrees, and that will give you that vertical height. That should help you with all of these problems. If you have any questions, let me know. Good luck.